Hi, so for today we are going to continue our discussion all about the 1001 solved integrals. This would be the part 5 of our 1001 solved integrals. So we're going to finish this. So we are still, I don't know, less than 10% of 1001, but we will try our best to actually solve this, okay? To finish this 1001 solved integrals. So let's get started. For our problem 41, we have the integral of 2x minus 5 dx all over x squared minus 5x plus 3. So what are we going to do is we are going to let u as x squared minus 5x plus 3. This is a simple u substitution because, as you can see, if we are going to differentiate u with respect to x, that would be 2x minus 5 with respect to the x, of which would be our numerator. So we have 2x minus 5 dx. We simply substitute as our du, and then our u is x squared minus 5x plus 3. So that would be du all over u. So that would be ln of the absolute value of u plus c, but we should substitute u to its original variable. So we have x squared minus 5x plus 3, then we have plus c as our answer for this number 41 problem. Okay, so let's try number 42. We have the integral of 1 minus 2x squared, 1 minus 2x squared. We have dx all over, we have x. So we have no other choice, but we have no choice but to actually get the expansion of the binomial here. Okay, so we have squared, 1 minus 2 squared. We expand this, that becomes 1 minus 4x, okay, and then plus 4x squared. That is the expansion of the binomial that we have in here. So, and that is divided by x dx. So we need first to simplify the given integral. So we know that this is separated by minus and addition signs, so we can separate them independently so that we can simplify. So we have integral of 1 all over x dx minus we have 4x all over x dx plus we have integral of 4x squared all over x dx. The properties of integral. So we have cancels, we have cancellations here. We have x squared all over x, so that our integral simply, we have 1 all over x dx minus, I can factor out 4, integral of simply dx, and I can also factor out 4. X squared all over x is simply x dx. So yeah, we can now integrate them independently. So we have 1 all over x dx, that is simply dx all over x, that would be the ln of the absolute value of x, minus 4 integral of dx is simply x, plus 4 we have integral of x is x squared all over 2, then we have plus c. So this becomes 2 also. So our final answer would be the ln of the absolute value of x minus 4x plus 2x squared, then we have plus c. So this would be our final answer for this given problem. Okay, that is our final answer for the problem 42, if I'm not mistaken. So for number 43, for our third problem, so we have 43, we have the integral of y dy all over, we have 1 plus y squared, if I'm not mistaken, raised to 4. So 1 plus y squared raised to 4. So there is no need for us to expand this, just like what we had did on the previous item. Why? Because if we're going to directly let u, we have 1 plus y squared, then we have derivative of u with respect to y, that becomes 2y dy. Of course, our y dy is present, so there is no need to actually expand this into fourth power. So I have y dy on my numerator. What I want here is y dy, so I have to isolate 2. So I have d all over 2 equals y dy. And now I can perform the u substitution. So we have y dy equals du all over 2 all over 1 plus y squared, that's u raised to 4. So I can factor out what? I can factor out 1/2. So we have 1/2 integral of du all over u raised to 4. And that is simply a power rule. So I have 1/2 integral of u raised to negative 4, and then we have du. By power rule, we have u raised to negative 4, that's u raised to negative 3 all over negative 3 plus c. So we have negative 1 all over 6 u raised to negative 3 plus c. Of course, we have to get back to original value. We have to substitute it back, the original value of u. That is negative 1 all over 6. Our u is 1 plus y squared raised to negative 3 plus c. So you can have it, your final answer is this, or you can choose to eliminate the negative exponent. So by getting the reciprocal of that becomes this. Okay? So you can also have this as your final answer. Yeah, so that is for our number 43 problem. Number 44. We have the integral of v plus 3 all over v minus 1 dv. So this is a little bit, let's say, tricky. Okay, because we need to rewrite this integral before we can actually integrate this. So as you can see here, you cannot use U substitution in here, nor partial fraction, nor IBP, or whatsoever. There's no such thing that we can do here. There's not much anything that we can do here. But what we can do here is a technique that we can force the numerator to become the same as the denominator. So we are going to force this v plus 3 to become v minus 1. So I'm going to write v minus 1 on the numerator. But of course, I have to add plus 4 in it. So that if we are going to isolate or simplify v minus 1 plus 4, that is technically still equal to v plus 3. Okay? So that's the whole thing. And I can regroup this, the integral, as v minus 1 plus 4 all over v minus 1 dv, so that I can apply the properties of integral. So we have v minus 1 all over v minus 1 dv plus, okay, because of the plus sign here, the integral of 4 dv all over v minus 1. So as you can see, this v minus 1 leads to 1. So we simply have on the left side of our term, we have dv, and then we can factor out 4 integral of dv all over v minus 1. So it's very, very, very simple. Okay? We know that if we let u equals v minus 1, that the du equals dv. So we can simply substitute this in order for us to integrate the integral of dv all over v minus 1 as du all over u. So we have v, integral of dv is v, plus 4 ln of the absolute value of u plus c. So, but we have to go back to the original variable. So we have v plus 4, the ln of the absolute value of u. What is u? That is v minus 1 plus c. So this would be our final answer. So the trick here is we are going always to force the numerator to become our denominator. We are going to force the numerator to be equal with the denominator, and that's what we did. We copy v minus 1, but we're going to add a number such that when we add it, it would still result to v plus 3, to the original numerator. So that is what we did here. That is one of the techniques that we need to learn in evaluating such integrals. For number 45, this will show you on how did they get the integral of the tangent of x dx in the formula. So we know that the tangent of x by trigonometric identity, that is equal to sine of x all over cosine of x dx. So that would be sine of x all over cosine of x dx. Okay? So that must be it. So if we are going to look at it carefully, sine of x and cosine of x has a what do you call this? Has a similarity with each other, has a relationship with each other. So if I'm going to let u equals cosine of x, okay, I'm going to get a derivative that is negative sine of x dx. Okay, so I only have sine of x dx here. So we have negative du equals sine of x dx. So I multiplied both sides of the derivative by negative 1. So we can now substitute. We have negative du all over u. So we can factor out negative, and then we have du all over u. That's how negative ln of the absolute value of u plus c. Okay? Integral of du all over u is ln of u, absolute value of u. So we have negative ln of the absolute value of u. What is u? That is cosine of x, okay, plus c. So in some other books, you would find that this is the value of the integral of tangent x. But some of the books, and this is still correct, if we're going to manipulate this, okay, we know that this negative 1 can be the exponent of the ln. So we have ln of the absolute value of the cosine of x, okay, raised to negative 1. So what happens here is we can apply the properties. So we have 1 all over cosine of x. We negate the cosine of x because of the negative 1. And 1 all over cosine of x is actually secant of x. Okay? The same is with the sine of x, that is 1 all over cosecant of x. So if we're going to substitute it, that would be ln of secant of x plus c. Any of the two is correct answer. Okay? So in some books you can see, in some reference we can see that the integral of tangent of x is negative ln of cosine of the absolute value of x plus c. Whereas on the other reference, that is ln of the absolute value of the secant of x plus c. That is still the same. Okay? Those two are the same. Okay? So yeah, that is the same. Okay, for our 46th problem, number 46. We have the integral of the cosine beta d beta. Beta is our variable here. 2 plus 3 sine beta. So if we're going to get the integral of this, we have cosine beta d beta plus 2 plus 3 plus sine beta. That is simply a U substitution. So we have to let u, we know that there is a relationship between the sine and cosine. So it's such that if we get the derivative of sine, that would be cosine. So we have 2 plus 3 sine beta. Then we get the du, that would become 3 cosine beta d beta, of which cosine beta d beta is here. So I can isolate 3 du all over 3 cosine beta d beta here. So if I'm going to do that, we have the integral of cosine beta d beta du all over 3 all over, we have 2 plus 3 sine beta, that is u. That is 1/3 integral of du all over u. And that is very simple because this integral will lead to a natural logarithm value. So we have 1/3 the ln of the absolute value of u plus c, and that would become 1/3 ln of the absolute value of 2 plus 3 sine beta plus c. So we can also write it as 1/3 ln of the absolute value 2 plus 3 sine beta raised to 1/3 if we want to simplify our expressions or our final answer. But I'll just leave it as it is. So for number 47, we have the integral of the cosecant squared x dx all over, we have 1 plus cotangent x. Okay, 1 plus, that is 1 plus cotangent of x. And that is still a simple U substitution because we all know that if we get the derivative of cotangent, that would result to a negative cosecant squared. Okay, so if we're going to let u this, we have to let u equals 1 plus cotangent of x. Then the du would be negative cosecant squared of x dx, of which we have cosecant of x squared dx here Multiplying this both sides by -1, this becomes negative du, and then we have cosecant squared x dx. So we can now simply substitute. So we have what? Negative du all over 1 plus cotangent of x, that is u. So you have negative integral of du all over u. That is very simple. So we have negative ln of the absolute value of u plus c. We have negative ln of the absolute value of u, that's 1 plus cotangent of x plus c. And this would be our final answer for this given problem. It's very easy as it is. Okay. So for number 48, that is our 8th problem for this. So we have dz all over this is 2 plus z. I think it is 2 plus z. So 2 plus z raised to 3 halves. So in this type of problem, we can simply use the property of the exponent. So we can negate this, or we can get the reciprocal of this and negate its exponent. So we have 2 plus z raised to negative 3 halves dz. Okay, so that is how simple it is. So of course, don't forget to have it U substitution, because you cannot really use power formula without using the U substitution. We have let u, we have 2 plus z du, that is dz. Okay, so we have transformed this into 2 plus z is u raised to negative 3 halves. Then we have du equals dz. So I have du. So that's power formula. Negative 3 halves plus 1 is negative 1 half. So we have a u raised to negative 1 half all over negative 1 half plus c. So that would be negative 2. Get the reciprocal of this. Okay, and proceed with multiplication with the u. In other words, we can rewrite this negative 2 all over u raised to 1 half plus c. That would be negative 2 all over u. What is the u? 2 plus z. 2 plus z raised to 1 half plus c. So this could be our final answer in doing that. It's very, actually, it's very, very simple integrals. So for our number 9, let's try to solve it again. For number 49 of the integral, we have x cubed dx x minus 1 all over x minus 1. So in this case, so in this problem, we're going to divide x cubed all over x minus 1. There is no way that we can directly use U substitution in here, because whichever we use, let's say x cubed, get the derivative of that, we have 3x squared. We don't have any x squared term in here. Okay, and if we let u as equal to x minus 1, then that would be simply dx. And where can we substitute this x cubed dx, or where can we substitute this x cubed? None. So we have no choice, but we can use synthetic division. So since this is x minus 1, my value would be 1, because we will be equating this into 0. Okay, and transpose, get the value of x, and then we have 1 as our divisor. Then x cubed, x squared, x, and then the constant term. So we're going to get the constant term of those. So we have x cubed, that's 1. And since this denominator or numerator does not have any x squared value, then its constant would be 0. And the same as with the x, there is no x in the numerator, and that is x. And there's no constant term, then 0 is the constant term. So synthetic division, we bring down 1, and then we multiply it by 1, and then we have 1 times 1 is 1. So we add here, that becomes 1. Same process. Then we add here 1, and then we have 1 plus 0 is 1. 1 times 1 again is 1. 0 plus 1 is 1. So this would be the exponent or the constant of your x squared. Since you divide x cubed with the 1x, this would be your x squared. and this would be the constant of your x, and this would be your constant. And this is, it does not have any remainder. Okay, the final answer does not have, is not equal to 0. So since it does not equal to 0, this one here would be 1 all over x minus 1. We haven't divided this one, okay, perfectly with the x minus 1. So we have this. So we have reduced now the given integral as the x cubed dx all over x minus 1. That is synthetic division. If you are confused, you should review your synthetic division or the division of polynomials. So we can rewrite this as x squared, okay, x squared plus x plus 1 plus 1 all over x minus 1. So that's how we are going to rewrite this. Okay? So after rewriting that, we can now separate. We all know that we can rewrite this as x squared dx plus integral of x dx plus integral of dx plus integral of 1 all over x minus 1 dx. Okay? So that would be our integral. So it's very easy. So we have x cubed all over 3 plus x squared all over 2 plus x. And this would be what? Plus natural logarithm of the absolute value of x minus 1 plus, of course, you have to use U substitution here. If you let u equals x minus 1, du would be dx. So this term would be du all over u. And then if you got that, that's ln of the absolute value of u. If you change u, that would be ln of the absolute value of x minus 1, which is basically the same as what we have written here. So that is our answer for our problem number 9. Okay, last problem for this video again. So number 50, we are 5% of the 1000. Okay, approximately 5%. So you have the integral of secant theta tangent of theta d theta all over, we have 2 secant theta plus 3. So 2 secant of theta plus 3. Plus 3. So if we're going to let u equals 2 secant theta plus 3. Why do we let u? Because we have in the numerator secant theta tangent theta, of which that is the derivative of secant. So we have 2 and then derivative of secant theta, that's secant of theta tangent theta, derivative of the constant 3, that is 0. So you have du equals 2 secant theta tangent of theta. Of course, we only have secant theta tangent theta, so I have to isolate 2. d all over 2 secant theta tangent of theta. So now I can perform the U substitution. So we have d all over 2 secant theta plus 3, which is equal to u. So you have 1/2 integral of d all over u. So in that case, we have 1/2 ln of the absolute value of u plus c. But u, we can substitute it back. So we have 1/2 ln the absolute value of 2 secant theta plus 3 plus c. That would be our final answer for this problem. Okay, so if you enjoyed this video, please don't forget to like, subscribe, and share my channel with your friends. I have playlists for integral calculus, so make sure to please tune in and please hit up the notification bell so you would be updated whenever I upload some videos. Okay, whenever I upload videos. So thank you so much, guys, for listening. Again, this is Jei Abat. See you again on the next video.